So, done with homework problems. Let's get the lecture started and pick up where we left off last time. And where we left off last time was talking about limits, the hardest concept we're going to talk about in this class. Before we talk about limits, let's remind ourselves of just what a sequence was. Because we were only taking limits of sequences. So what is a sequence? What's a sequence?
It's like multiple things in order, right?
Multiple things in order. We had a precise definition for a sequence. A sequence is a function whose domain is all the positive integers. So remember, a function set of ordered pairs. So a sequence, it takes 1 and it maps 1 to something. It takes 2 and it maps 2 to something. It takes 3 and it maps 3 to something. Dot, dot, dot. And it does it for every positive integer. As a general rule, we use this kind of notation to talk about sequence, x sub n, for some arbitrary sequence. When your sequence follows a nice pattern, maybe it's 1 goes to 1 over 1, 2 goes to 1 over 2, 3 goes to 1 over 3, etc. When it follows a nice pattern like that, then we would have said x of n is equal to 1 over n. How do you get what n was paired with? It was paired with 1 over itself. So there's one sequence. So if we agree ahead of time that we'll write whichever term 1 is paired with first, and whatever 2 is paired with second, and whatever 3 is paired with third, we also often write the sequence as 1 over 1, comma, 1 over 2, comma, 1 over 3, dot, dot, dot. Where it's understood that the first thing is what 1 went to, what 2 went to, what 3 went to. So let's write out one more sequence. Let's say that I said our sequence is equal to, well, we'll just look at the sequence. When we just write generic sequence, we put it in curly braces like this. Let's look at the sequence n plus 1 over n. What is this sequence?
It's just, it's on
1 plus 1
plus 1 divided
It's
by
2 over
itself.
1,
2 over 1,
3 over 1, or 3 over 2,
3 over 2,
and so on.
4 over 3,
4 over 3, 5 over 4,
5
6
over 4.
5.
There you go. Dot, dot, dot. There it is. How many terms are in a sequence?
A lot.
Infinite. Always infinite. Pairs every positive integer with something.
Right.
Eventually, 1,564,251,561 gets paired with something. Every positive integer gets paired with something. There's infinite terms in a sequence. Now, some sequences have this property that they keep getting closer and closer and closer and closer and closer to a particular number.
Right.
In this case, what's the particular number? 1. If we were to keep going down this, then we would have eventually gotten 1, 0, 0, 0, 0, 0, 0, 0, 1, all over 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0.
Right.
Which is 1.0.
It's pretty close to 1. Right.
Ridiculously close to 1. And as we keep going, we keep getting even ridiculously closer to 1. That was intuition for what we meant by this sequence converges to 1. The limit of this sequence is equal to 1. The way we would have written that is, keep right here, we would have said the limit as n approaches infinity, as n gets absurdly large, of our sequence n plus 1 over n is equal to 1. Now, we gave this thing, this type of notation, a proper definition. And I gave you the full-blown, big boy calculus definition of what a limit is.
Right.
So let's give you that exact definition again and try and make it quick with our intuition again. We say that the limit as n approaches infinity of some arbitrary sequence x of n is equal to x. So this is the notation we're defining. So this is logically equivalent to. So colon, this side's our definiendum. It has a new notation we're defining. Our definiends go over here, notation that we already know and understand. So what does this mean? It means that for every positive number epsilon, so for every epsilon in the positive real numbers, there exists an index in the sequence. So there exists big N in the positive integers. There exists some index in the sequence such that the distance from our sequence to the point it's supposedly getting closer and closer to is going to be less than epsilon from that index onwards. Let's read it again. What does it mean that my sequence converges to x? It means that for every epsilon in the positive real numbers, or in other words, for any distance you choose, no matter. Epsilon is just a variable here. We typically, as a Mayer notation, the same way that I typically use like an A, a B, and a C to represent a constant, an X, a Y, a Z to represent some variable real number. Epsilon represents a really small positive number.
Okay.
So like 1/1,000,000,000th.
Right.
Okay, so for every really small number you choose, I can always find some point in the sequence, some index in the sequence, some big N in the sequence,
Right.
such that the distance from the sequence to that point is less than the really small distance you gave me
Right.
from that index onwards, as long as we're going past that index. Let's get a pacer for this.
That makes sense. Actually, that's.
So here's our x. And I've got some sequence here. We'll write out the sequence in blue dots. Here's x sub 1. Here's x sub 2. Here's x sub 3. Here's x sub 4. X sub 5. X sub 6. 7. 8. 9. 10. 11. 12. 13. 14. 15. 16. 17. And now it's stupid to try and draw it. Here's our sequence. Our first term we usually represent with x sub 1. This is what 1 went to. So maybe it's 1/3 or whatever. This is x sub 2. This is x sub 3. This is x sub 4. X sub 5. X sub 6. Etc. You get the point. Let's write one more. 7, 8, 9, 10, 11, 12, 13, 14, 15. Here, right here we had x sub 15. If this sequence gets arbitrarily close to this green x, then that means for any distance you choose, I should always be able to find some point in my sequence, maybe it's x sub 15, such that from that point onwards, I'm within whatever distance you specified of x.
Right.
So you say, I want you to be within an inch of x. So that would be all the points from like right here to right here.
Right, because.
And I say, no problem. Look, starting from x15 onwards, we're always within an inch of x. I could have started from x sub 12, but I don't need to find the first index. I just need to find some point in the sequence, such that from that point onwards, I'm always within whatever distance you specified of x. And then you can pick a new distance and we can play the game again. You might say, okay, 1/1000th of an inch. I say, okay, starting from x sub 10,000, we're there.
Right.
And you might say, okay, within 1/1,000,000th of an inch.
Right.
And I say, okay, starting from here. So for any distance you give me, I can always find a point in the index such that from that point onwards, I'm always that close
Right.
to the thing we converge to.
You never make it, but you're always, that close.
Right, we get arbitrarily close. So let's really quick do just a simple proof. You won't have to reproduce any of these. We're doing a much bigger deep dive than the author does into this. But just to give you a taste for how these things go. So I'm going to prove, I don't know, which one should we do? Let's start with just simple. Let's just prove that the limit as n approaches infinity of 1/n is equal to what?
1/1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7.
So in the limit, what does it equal?
0.
0. So I'm going to do proof. Proof that this is in fact the case. How do I prove this? What I need to do is, 1, let epsilon be any positive real number. This is some number you get to choose. I don't get to choose what this number is. I need to show that this condition holds for any epsilon you pick. So let epsilon be some positive real number. I have no clue which real number it is. You with me?
Yeah.
Now I'm going to have to introduce you to something called the Archimedean property. The Archimedean property on the positive integers, on the natural numbers, is that there is no biggest integer. That's the Archimedean property. There's no biggest integer. There's no biggest number. Any number you pick, I can always find one bigger. If you say no, x is the biggest number, I say what about x plus 1?
Right.
X plus 1 is also a number, it's bigger than x, there's no biggest number. Archimedean property. Okay, so 2. Observe that there exists big N in the positive integers such that N is greater than 1 over epsilon. Kind of a funny way to say it. So epsilon's,
Read that again, will you?
Observe that there exists big N in the positive integers such that big N is greater than 1 over epsilon.
Okay.
So the thinking here is typically the epsilon we're thinking about is going to be a really small number.
Right.
1 divided by a really small number is a really
Small number.
a really big number. 1 10,000, 100,000 is really small.
Right.
1 divided by that, how do you divide by a fraction? You multiply by its reciprocal.
Oh.
So that's equal to 100,000. Did I do it wrong again? Yeah. So that's equal to 100,000. Or another way you can think about it is, if I take a 1 and I divide it up into 100,000 pieces, how many pieces do I have? 100,000 pieces.
Right.
Okay, so if epsilon is a really small number, 1 over epsilon is going to be a very
Big number.
big number. But it doesn't matter how big that number is, I'm always guaranteed that there's a bigger number.
Right.
You with me?
Yeah.
Yeah.
So big N is for sure bigger than 1 over epsilon, whatever that is. I know that such a number exists.
Right.
So there it is. Okay. 3. Then 1 over n minus 0. This is doing x of n minus x. My sequence minus what converges to.
Right.
I'm going to prove that this is less than whatever epsilon you chose from this index onwards.
Right.
That's what I'm going to show now. So 1 over n minus 0 is equal to what? When I subtract 0 from something, what am I left with?
You just symbol.
Same thing.
Same thing. So it's still just the absolute value of 1 over n. N's always a positive number, so 1 over n is always positive. The absolute value of a positive number is just that number.
Right.
So this is just equal to 1 over n.
Right.
Now, I know that 1 over n is going to be less than 1 over big N as long as my little n is greater than or equal to my big N. Less than or equal. If I make my denominator bigger, my number gets smaller. 1 over 10,000 is less than or equal to 1 over 1,000.
Right.
So as long as my little n is greater than or equal to my big N, then 1 over little n is going to be less than or equal to 1 over big N.
Right.
But I know 1 over big N is less than epsilon. Sorry, should have worked out that algebra from here. Observe that there exists big N in the positive integers such that big N is greater than 1 over epsilon. That gives, multiply both sides by epsilon, divide both sides by big N, and I get that 1 over big N is less than epsilon. These say the same thing.
Right.
Okay. So then, I know that this is equal to this is equal to that is less than or equal to 1 over big N is less than epsilon for all n greater than or equal to big N. So I just barely showed that that distance is less than epsilon for all n greater than or equal to big N. 4. Therefore, the limit as n approaches infinity of this thing, 1 over n, is equal to 0. That's what we just proved. Now this gives us our procedure for how to pick the index for any epsilon you give. So let me show you what this proof is telling you. Pick an epsilon. Give me any small number.
1
quadrillion.
One I can write on the board.
1 million.
1 1,000,000. So if epsilon is equal to 1 over 1 million, then I say, look, just pick an n bigger than 1 over 1 million. So I say an n then that we can choose is, let's pick the index, 1,000,002. There's my big N. Then I say, notice that this happens. 1 over 1,000,002 minus 0 is going to be less than 1 over 1,000,000.
It's going to be less than?
Uh-huh. Let's write that out. So I'm saying 1 over 1,000,002 minus 0 is going to be less than 1 over 1,000,000.
Oh, yes, correct.
And same with, if we replace that with 3.
Or 1.
Well, no, we're starting at 2. We're starting at big N. It turns out 1 could have worked, but that's not what I'm saying.
Okay.
So I'm saying it works for 1 over big N, and 1 over, and any little n greater than or equal to big N. So I'm saying it's true when we do it with 2, when we do that with 3, when we do that with 4, 5, 6. Keep counting up from there, and this will be true from that point onwards.
Right.
And so this proof tells me how, for any epsilon you choose, how to come up with the index such that from that index onwards, this inequality will be satisfied.
Right.
That's exactly what it means to prove that its limit is that point. So read this one more time, and I think you'll probably get it. What do we mean when we say the limit as n approaches infinity of x of n is equal to x? That means that for any small distance you choose, I can always find some index in the sequence, such that my sequence is less than that distance away from x from that point in the sequence onwards. Feel like you got it?
I think so. Yeah.
It's dense. There's a lot to get there. Okay, so now we're going to prove a couple properties about limits. We're going to prove that the sum of the limit is equal to the limit of the sums, the difference of the limit is equal to the limit of the differences, that if we take a sequence, let's just explain it one at a time as we go. Maybe leave the definition there. So first thing we're going to prove is that if I'm going to stop doing the limit as n approaches infinity and just do limit like this. If the limit of an is equal to a and the limit of bn is equal to b, comma, then the limit of an plus bn is going to be equal to what?
A plus B.
A plus b. That's all we're proving here. Concrete example of that, if I did the limit of 1 over n, if I was looking for the limit of 1 over n plus the limit of n plus 1 over n, then we could just evaluate this as two separate limits. I could say this gets closer and closer to 0, this gets closer and closer to 1, and so the total limit is 1. That's what this proof is going to enable us to do.
That's cool.
Okay, so that's the big idea of the proof. So let's do the proof of it. So 1, assume that the limit of a sub n is equal to a, and the limit of b sub n is equal to b. My job is to prove that the limit of a sub n plus b sub n is equal to a plus b. That's what I'm trying to prove. Okay. So, how do we prove that? This exact definition. I need to show that for any epsilon you choose, I can find an index in the sequence such that this distance is less than whatever distance you gave me from that index onwards. So 2. Let epsilon be any positive real number. Know nothing about it except for that it's a positive real number. Now, I know that an converges to a. That's given to me. I know that the limit of my sequence an equals a. So I know that an satisfies this definition already. So I know that then there exists, I'll call it n sub 1, in the positive integers, such that the distance from a sub n and a is less than any distance I choose for all n greater than or equal to n sub 1. I already know that an converges to a. That was given information. So for any small distance I choose epsilon over 2. That's a small distance. There must be some point in the index such that this distance is less than the small distance I gave it from some index onwards. I'm calling that n sub 1.
Okay.
So I know that is true since the limit of a sub n is equal to n. Similarly, I know that there exists n sub 2 in the positive integers such that the distance from b sub n minus b is less than epsilon halves for all n greater than or equal to n2. Because b sub n converges to b. So there's got to be some index in the sequence such that from that point onwards, this distance is always less than any small distance I give it.
Right.
Okay, perfect. So now I'm going to define my big N. Let big N equal the max, whichever is bigger, out of n1 and n2. So since n is the max of these two numbers, and since this is true from big N1 onwards, and this is true from big N2 onwards, both of them are going to be true from big N onwards, because it's whatever is bigger of the two. If this was true from 100 onwards, and this was true from 1,000 onwards, then they're both true from 1,000 onwards.
No.
If this is true from 100 onwards, then that means it's true for 100, and 101, and 102,
Right.
and 1,000, and 1,001, and 1,002. So if they're both true, if this is true from N1 onwards, and this is true from N2 onwards, then they're both true from big N onwards.
Okay.
You with me?
Because n is bigger than n.
It's whichever bigger out of those two numbers.
Right.
Okay, so then finally, 5. Then, let's see what we're trying to prove. Remember what we were trying to prove. On the side, maybe put up here, I'm trying to prove that the limit of an plus bn is equal to a plus b. That's what I'm trying to prove, right? The way I do that is I need to show that the distance from my sequence to the point they converge to is less than epsilon. So I'm trying to show that my sequence, which is an plus bn, minus the point I'm saying it converges to, which is a plus b, that distance I need to argue is less than epsilon from big N onwards. And if that's the case, we're done.
Right.
Okay, so what is this equal to? I'm going to reorder the terms. Distribute that negative to both those, so that's a negative a and a negative b. I'm going to group the negative a with an and the negative b with bn. So this is the same thing as an minus a plus bn minus b. Like that. You with me?
Yes.
Now we're going to use what's called the triangle inequality from absolute values. Back when we went over this, I proved it for you. How to do the triangle equality for absolute values. In short, it says that the absolute value of a plus b is always less than or equal to the absolute value of a plus the absolute value of b. Okay? So I'm going to use that. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. You with me?
Uh-huh.
But now I know that am plus a is less than what?
N.
Oh,
minus
sorry. I put a plus sign there. This is a minus. Minus, minus. So the distance between an and a is less than what?
We know that's greater than, it's less than
It's less than epsilon halves from big N onwards. Ultimately, we're going to say this expression is true for all n greater than or equal to big N. So we're going to tack that on at the end. So this distance is less than epsilon halves, and this distance is less than epsilon halves.
Right.
So that is going to be less than epsilon halves plus epsilon halves. The epsilon halves plus epsilon halves is equal to
Epsilon.
epsilon for all n greater than or equal to big N. So there it is. As fairly showed that the sequence minus the point it converges to is less than epsilon from some index onwards. So, if an converges to A and Bn converges to B, then An plus Bn converges to A plus B.
Right.
Or the way that we say that is the limit of the sums is the sum of the limits. The limit of the sum is equal to the sum of the limits. Because this is the limit of that and this is the limit of that. The limit of the sum is equal to the sum of the two limits. With me?
Yeah.
Okay. This is the only one I'm going to prove all the way. These are calculus proofs, not geometry proofs.
Yeah.
They're even deeper than calculus. These are real analysis proofs. Real analysis is derived in calculus, so this is deeper than calculus. But, so, showed you one, full throttle. All our limit rules are this. The limit of An plus or minus Bn is equal to A plus or minus B. So if you did the difference of the sequences, it gives you the difference of the limits. The limit of An times Bn is equal to A times B. And finally, the limit of An over Bn is equal to A over B, where B is not equal to 0.
Right.
And it's actually more crucial than that. It's really that Bn can't ever be 0. So that sequence can't have 0 in it. Otherwise, one of the times you divide it, it comes out 0.
Right.
So those are our limit rules. Okay. So now let's jump into the actual using of these limits. So that was 11-5. Sorry, my page flipped on me. Limits.
No,
11-5.
What 11-5? Wasn't there?
Sorry, not 11-5 theorem, 11-5 section. So they give our first definition of 11-5, which is defining a sequence. All right, we already did that.
Oh, okay, I see what you're
Definition 11-6 is giving the definition of the limit. And notice that he is going to give the high-level definition of a limit. What does it mean to say that the limit of 1 over n is equal to 0? The author is going to give language of, it means it gets arbitrarily close to 0. He's going to leave it at that. He's definitely not going to give you full-blown, there's a definition of a limit. Okay, so we covered that. Theorem 11-10 is he's saying the limit of the product is the product of the limits. Theorem 11-11, he's saying the limit of the quotients is the quotients of the limit. So we wrote both those out right there. He doesn't prove either of them. He's telling you that these are results from calculus or real analysis. So just giving you high-level intuition. All the author is concerned about is giving you enough intuition that you can see what a limit is without actually calculating it. That's all he was trying to get you to the point of, which is we already got you comfortable with some of that just by looking at terms. So basically he wanted you to be able to do stuff like this and not actually be able to prove that that's the case. Just be able to kind of see it. So that's all he was after. Okay. So with that, we finally get to the definition of circumference. So our definition now of circumference.
That's interesting.
We start with the circle. I'm going to give you the idea, and then I'm going to give you the full-blown definition.
So you're just going to teach us still so we don't have to do homework on it?
Sorry, what?
According to the syllabus, you don't want us to do homework on past 11-8.
That might be the case.
Okay.
I don't know. I'd have to re-look at it and see what my thinking was. All right. So we've got some circle here.
Okay, right.
And we can inscribe inside of that circle a triangle.
Triangle, polygon, etc., etc.
Perfect. Yeah, you've already got the idea. So we can inscribe in that triangle a 3-sided polygon, piece of 3. And it will have its corresponding perimeter of that polygon. which would be the distance from here to here, plus the distance from here to here, plus the distance from here to here. We know how to calculate distances of segments, lengths of segments. That's all well defined.
Right.
So P3 would have L3 as its length. And then,
We divided those in half.
that's one way to think about it, but we're actually just going to take this one at a time. So there's our three-sided inscribed polygon, and it has its length. Now I look at the four-sided inscribed polygon.
We went over this last time, didn't we?
Yeah, I already touched on this with you at the very start of the chapter to tell you where it was all going and why we were using limits.
Oh, that's right.
And then, so with a regular four-sided polygon inscribed in there, it's going to have a length L4. And then you can do a five-sided inscribed polygon, a six-sided, a seven-sided,
Et cetera, et cetera, et cetera.
et cetera, et cetera, et cetera. And we have corresponding L sub 5, L sub 6, L sub 7.
L is what?
L is the actual length. P is the polygon. P represents the actual shape. L represents the
Length of
perimeter.
L-
That's the notation I'm using. Maybe the
L
author does it
represents
slightly different.
perimeter, right?
Huh?
L represents perimeter.
L represents perimeter. P for polygon, L for length. Sorry,
You're good.
not P for perimeter.
Right.
Okay, anyways, and we can keep going up until we split this thing up into something like 100 pieces. And so if I were to break this up into a 100-sided regular polygon, doing all those sides, all the way around here. As we do that, we're getting a better and better,
Closer to a circle.
closer and closer to a circle. The perimeter of our polygon is getting closer and closer to the actual circumference of the circle. And so now our definition is circumference is going to be defined to be the limit of this exact sequence, of this L sub n. So whatever that goes to in the limit is our circumference. That's its definition. Does that make sense?
Interesting. We have a concrete example of that.
Oh, he uses P sub n for the actual perimeter. So pretend that P actually represents perimeter. He's going to do P sub n here, rather than thinking about the polygons and then the perimeter. So just P sub n, like that. That's the definition he's going to have. Can we have a concrete example?
Yeah. The circumference equation.
It's not an equation. You just see how to get better and better approximations of this thing. So right now, I should be able to just ask you, what's the circumference of a circle? And you know that. But what you should know is that you can get a shape that inscribes the circle, a polygon that inscribes that circle, and you know how to calculate the perimeter of that polygon.
Right.
And as you pick bigger and bigger polygons, then you're going to get a better and better approximation. And what that goes to in the limit, we're calling the circumference. You're saying, what's the numerical value of that thing? Or how do we calculate the numerical value of that thing?
Yeah.
So this is how the ancient Greeks, well, we haven't gotten to pi yet, but to get to pi, you have to approximate circumference. It pretty much comes down to that. And so the way that the ancient Greeks would approximate it is they would inscribe these shapes and manually calculate the perimeter of that shape that they inscribed. And that's how they did it. So we won't bother doing any of that, but I'm not sure how to give you a concrete example. Because this is just the definition of the circumference of the circle. It's what this sequence's limit is.
And P is the length of the perimeter.
Yeah, so P represents the perimeter. So notice two things. The perimeter, for one, is always getting bigger as you pick a bigger and bigger shape. The perimeter of the square that I inscribed in there has a bigger perimeter than the perimeter of the triangle.
Right.
And the way that you can easily see this is going from 4 to 8 sides, you can see how the perimeter must be getting bigger. Because if I had a square inscribed in here, and I were to compare that to the octagon, how do I get the octagon? I split that in two and do this. That's part of the conversation we were having earlier in the chapter. And since it took that side and broke it into those two sides, the hypotenuse of that right triangle has to be bigger than that side. The hypotenuse of that right triangle has to be bigger than that side. And so we had to have made it bigger every time. So if you keep splitting in half, you can for sure easily see that the perimeter keeps getting a bigger and bigger number. Second thing you notice is that the perimeter never gets past some limiting value. The perimeter will never be as big as the square that I circumscribe this circle in. So whatever the perimeter is, it's bounded from above by some number, but the sequence keeps giving us a bigger and bigger number. So the sequence keeps giving us a bigger and bigger number, it's approaching some number, but it never gets bigger than some other number. So it's in some sense sandwiched. And so that number that the sequence keeps getting closer and closer to, we call the circumference of the circle. It's the limit of those perimeters of those inscribed polygons. That make sense? Okay. So, So first theorem. The circumference of two circles are proportional to their radii. So we need to remember from last time, hopefully you remember some of these relationships. Last time we proved that given any two circles, that the radius, that r over r prime, was equal to the apothem over apothem prime, was equal to, what else did we put here? Oh, this was for any two polygons. Was equal to the perimeter of the polygon over the perimeter of the prime polygon. Do you remember proving these relationships for any two regular polygons that were similar? So if I had a hexagon and a smaller hexagon, these are meant to be similar. The radius of this hexagon has radius r. The apothem of this hexagon is a. And its perimeter is p sub n, since it's an n-sided polygon. And if I had a similar polygon here, with radius r prime, apothem a prime, and its perimeter is p sub n prime, then all these relationships are whole. They're all proportional to each other. Do you remember those proofs?
I think so.
It's what we ended with last time. And we also showed that their area was proportional to the radius squared, and their area was proportional to the apothem squared.
Right.
Okay. So we're going to use those relationships. What are we now trying to prove? We're now trying to prove that given any two circles, so given a small circle and a big circle, small circle has radius r prime, big circle has radius r, I am trying to prove that r over r prime is equal to the circumference over the big circle divided by the circumference over the small circle. In other words, the radii are always proportional to the circumference.
Right.
That's what we're trying to prove. You with me?
Yeah.
Okay. So I know that for any inscribed polygon I put inside of here, so if I put an n-sided polygon in both of these, if I were to put that in both of them, then I already know that p sub m prime, what I put inside of here, is equal to, over the perimeter of the polygon I inscribed in there, is equal to the radius of this one over the radius of this one, right?
Right.
That's using what we had last time. And this is true for any n-sided polygon I put inside of there. Now, if this is equal to this, sorry, I usually put the primes on the bottom. Let's stay with that. If this is always equal to this, then the limit of this, well, let's break this out one step at a time. So now I'm just going to write out all the algebra. The circumference over the circumference of the small circle is equal to, by definition, this is the limit of its inscribed polygons.
Right.
And this one is the limit of its inscribed polygons. Right?
Right.
And I know that the limit of a quotient is a quotient of the limit, as long as the denominator is never 0. I'm never going to get a 0 perimeter for inscribed polygons.
Right.
So this is equal to the limit of p sub n over p sub n prime. Limit of the quotient is equal to the quotient of the limit. With me?
Yeah.
Now, I know that p sub n over p sub n prime is always equal to r over r prime. So this is equal to the limit of r over r prime. R over r prime, those are two constants. Let's put a pin in this for a second and let me ask you something. What is the limit of this sequence? 2. So the sequence 2, 2, 2, 2, 2, 2, 2.
2.
What's its limit?
2.
2. The limit of a constant is just that constant. So we're saying the limit of a constant. It's just a number in there. So that's always equal to just that constant. And so we get C over C prime is equal to R over R prime. You with me?
Yes.
Now, doing some algebra, if I know that A over B is equal to C over D, I can swap those two and it's still true. Multiply both sides by B, divide both sides by C. And you're left with A over C is equal to B over D. Let's do a concrete example. I know that 2/3 is equal to, let's see, give me another way to write 2/3.
4/6.
4/6. That's kind of an easy one. Let's try something a little bit bigger. 8/12 maybe?
Yeah.
Okay, so if that's the case, swap these two and it's still true. That means that 2/8 is equal to 3/12. This is going back, we proved all this stuff with quotients early on. Not early on, but like 2 weeks ago.
Right.
Remembering some of this stuff?
Yes.
So, if I know that C over C prime is equal to R over R prime, I can swap those two. And so I know that C over R is equal to C prime over R prime. And there's our big old amazing result. No matter the circle, its circumference divided by its radius is always the same. The circumference divided by the radius of this circle is always equal to the circumference divided by the radius of this circle.
That is pi.
And that's true for any two circles you choose. That ratio always holds. And so yes, we now define pi. Pi is defined to be that ratio. Since we proved it's the same ratio for every single circle out there. It always comes out to the same number. We can define that number to be pi. Now we don't know what that number is. This doesn't tell us 3.14159 blah 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 blah. That's a numeric approximation of the value of pi.
Right.
This is its definition. And so you see, if you pick some circle, and if you can approximate its circumference, then divide by its radius, you're able to approximate the value of pi. So that's how the ancient Greeks would do it. They come up with approximations for circumference, divided by the radius of the circle they were using, and that would give an approximation for pi. Make sense? Okay, so next I think we're going to prove the area of a circle or something like that. Let's see, the circumference, we did that. Theorem 11-4, if C is the circumference of a circle and D is the diameter, the ratio of C to D, oh, sorry, I lied. This is not the definition of pi. But what we proved here is true. Circumference divided by radius is the same for any two circles.
What's pi then?
Now, this would also be, notice that,
Circumference over diameter.
yeah, circumference over diameter.
Oh.
Notice that multiply top and bottom of this by 2 doesn't change it. So this is equal to 2r over 2r prime, which is the same thing as the diameter of the big one over the diameter of the small one. And now you can swap that and that, and you get C over D is equal to C over D prime. Okay. Circumference over diameter is pi, not over radius. Can't believe I said that. Which you can start to see what that should roughly be. What's one really dumb way that you could approximate this? You take some circle, take a string across the diameter, and then you take the string and see how far it gets. First time running the string around might get that far. Second time running the string around might get you that far. Third time running the string around might get you that far. So you might say it's 3, and then guess how much of the string is left. That's like a really dumbed down way to start approximating this value of pi. Make sense? Okay, but circumference over diameter, there's the exact definition of pi. Okay, did that. If C is the circumference of a circle and D is the diameter, the ratio of C over D is the same for all circles. We already proved that. We define that to be pi. That's definition 11-4. So formula now for circumference. What's a formula for circumference we can use? If pi is equal to circumference over diameter, we can say that circumference is equal to pi times the diameter. So circumference is pi times diameter, or if you want in terms of the radius, since the diameter is 2 radiuses, we often write this as 2 pi r. That's the common way that we write the circumference of a circle. 2 pi r. That's where that formula comes from.
Right.
Make sense?
Yeah.
Okay. That was that corollary. How how to approximate pi. You can look at section 11.7. He goes over some actual calculations and approximation of pi. I don't think it's too interesting because you get an easy formula from calculus that we can use to get an arbitrarily good approximation of pi. And the formula you get from calculus, if you ever take calculus 2, that formula will be that pi force is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13 dot dot dot, going on forever. And so you can do this calculation to your heart's content to get as good approximation as you want. Or if you're trying to calculate pi, just multiply both sides by 4. And so you get pi is equal to 4 times that. And you'll learn about that in Calc 2. But so this is like how we actually get an approximation for pi and get as good as we want, rather than trying to inscribe shapes in a circle. Huh?
Why do you do it by 4?
So what I have before gives you an approximation of pi force.
Pi force. Okay.
Pi force for the arc length, or not for, sorry, I don't have a good way to say it. That's just what, when you come to calculus, you're going to approximate pi force, and then if you want pi, you multiply both sides by 4. Okay, so, but it's a pretty easy formula to memorize. You can see the pattern there, so if you ever need to approximate the value of pi to your heart's content, there it is. Or you can just Google it. Okay, now we get to area of a circle. Theorem, given a circle C, that denote the area of the inscribed regular polygons. Okay, so we're getting to the area of a circle. So let's prove the formula for the area of a circle. You know the formula for the area of a circle?
Yeah. No. Yeah.
On top of my head.
Area of a circle, pi r squared.
Yeah.
So that's what we're going to prove next. So we're trying to calculate the area of a circle. So we've got some circle. And what we do is we divide this circle up into regular polygons, and we calculate the area of the regular polygons. And then the area of the circle is going to be the area of the limit of those regular polygons. Does that make sense? So I'm going to break this up into regular polygons where I use break it up into tons of pieces. So I break this circle up into basically tons of triangles, right? That's going to give me a regular polygon. And then I calculate the area of each of these little triangles and add up the area of all the little triangles, and that's going to give me the area of the circle.
Yeah.
So a sub n, we're going to use to represent the area of an n-sided regular polygon inscribed in the circle.
So is the height of that triangle is the radius, right?
The height of this triangle, remember the triangle doesn't go all the way to the top. There's going to be a teeny bit of space there. So the height of that is going to be the apothem of our regular polygon, not the radius. This is going to be the radius. This is r. This distance right here is going to be a sub n. Why do I say a sub n? Because it's going to change depending on our regular polygon. So if we were to do a really dumb case and do the case of a sub 4, what would we use?
Square.
A 4-sided polygon. We'd be looking at these triangles right here. This right here would be my a sub 4. And we would calculate the area of that triangle and multiply it by 4, and that gives me the area of the whole thing. So that is how we would calculate big A sub 4. Big A sub 4 would be the area of that thing. Big A sub 5 would be the area if I used a 5-sided figure. Up here, I've got, I don't know, like A sub 30 being drawn out or something like that.
Right.
But this is just meant to be an arbitrary one. So how do I calculate the area of some A sub n? That's what we're going to figure out. And then the area of the circle, by definition, we're going to define the area of the circle. The area of the circle is going to equal the limit of the areas of all these n-sided regular polygons. So we're going to figure out the limit of these n-sided regular polygons and use that to figure out the area of the circle. You with me? So first, I need a formula for the area of these n-sided polygons.
Right.
Let's go back to the case where it was a sub 4. So let's write big A sub 4. How would we figure out this thing's area? Well, we know it's the height of its apothem.
Right.
So it's the height of its apothem. So that's a sub 4. Well, let's see. 1/2 the base times the height of this triangle, and then multiply the whole thing by 4. You with me?
Yeah.
So calculating the area of that little triangle, that's going to be 1/2. Its base is 1/4 the perimeter. So the perimeter of the 4-sided polygon divided by 4. 1/2 the base times the height. And this will give me the area of that triangle. And then if I multiply that whole thing by 4, then that would give me the area of that square there. You with me?
Yes.
Let me draw this out one more time now for an 8-sided figure, just to make sure we're completely on the same page. Okay, not very proportional, but you get it.
Yeah.
So this right here would be a sub 8. That's our apothem for this 8-sided figure.
Right.
So the area for a sub 8 would be equal to, we do 1/2. What's the base? What's this distance right here? It's going to be 1/8 of the perimeter.
Right.
So it's the perimeter of the A-sided polygon divided by 8. That gives me the base of one of these triangles.
Times
So
your
1/2 the base times the height times a sub 8
times 8 is your
times 8
is your area.
is your area. Perfect. So a sub n now. Now see if you can help me figure out a sub n. What is a sub n going to be for up here?
1/2.
So it's going to be 1/2 times
piece of n
p sub n, the perimeter of the whole thing,
over n
over n
times 8 sub n.
times a sub n, all times n of n, right?
Right.
And so that's the limit we're trying to evaluate. We're trying to evaluate what is the limit as n approaches infinity of a sub n. We're trying to figure out what this is. Well, this is going to be the same thing as the limit as n approaches infinity of 1/2 times p sub n over n times a sub n times n. Right? Sorry. Let me know if I'm losing you in this.
Oh, not yet.
Okay, what do we notice? Does anything cancel?
P then A.
No, you can't cancel those. But look, we have an n in the denominator and an n in the numerator. I can cancel out that n with that n. And so this is equal to the limit as n approaches infinity of 1/2 times p sub n times a sub n. Like that, right? You with me?
Go back.
So I cancel the n's out.
Right.
So we have 1/2 still. I have p sub n still. And I have a sub n still. Everything but my n's. Okay. So now, the limit of a product is a product of the limits.
Right.
So I can calculate the limit of each of these individually. So this is equal to, what's the limit of 1/2?
Limit of 1/2.
Yeah.
1/2.
Yeah. What's the limit of 1/2? 1/2. The limit of a constant is just a constant.
Oh, it's constant, right? Sorry, I thought you said like 1/n.
Right, just 1/2, just a constant.
Okay.
What's the limit of p sub n?
P sub n.
P.
P sub n.
What? Remember, p sub n is the perimeters of our n-sided polygons. As I do more and more points in here, what does the perimeter get closer and closer to?
Circumference.
Circumference. That's what circumference is. It's the limit of those perimeters by definition is circumference. So the limit of this is c. And now we just got to figure out the limit of a sub n. So I'm just going to write this times the limit of a sub n, and we still need to figure out what that is. You with me?
Yes.
So we got to come back and, so I'm going to look at this picture to figure out a sub n. So up here, looking at this, I'm going to solve for a sub n really quick. What was the base right here? We already calculated the base here.
The base is
It's just the perimeter divided by n.
right.
So the base right here is p sub n over n. Like that, right?
Right.
So half the base would be 1/2 of that.
Right.
So I'm using the Pythagorean theorem. I know that an squared plus half the base squared equals r squared. You with me?
Yeah.
So I'm going to write a sub n squared plus this whole thing squared plus 1/2 p sub n over n squared is equal to r squared. With me?
Yeah.
Okay, so now solving for my a sub n, I'm going to get a sub n squared is
And
equal
it's
to,
squared because of area.
it's squared because I'm just using the Pythagorean theorem so far.
Oh, right. Okay.
Just using Pythagorean theorem. All right, so now move this to the other side, and I'm also going to square it. So moving it to the other side is going to make it negative. 1/2 times 1/2 is 1/4 times p sub n times p sub n is going to be p sub n squared, whatever that is, all over n squared. You with me?
Yes.
So now, take the square root of both sides, and I get a sub n is equal to the square root of r squared minus p sub n squared all over 4 times n squared. You with me?
I think so.
Alright, so now we take the limit of that thing. So now we're looking at the limit as n goes to infinity of a sub n. What is that going to equal? As n goes to infinity, what happens to r? R is r is r is r. It doesn't change anything.
Right.
So we still have square root. R is still just going to stay r, so that's still r squared, minus p sub n squared as n approaches infinity. What's that going to approach?
Infinity.
No. What is
Circumference.
p sub n? Circumference. So that's going to approach the circumference squared, all divided by 4 times. As n approaches infinity, what does n get closer and closer to?
Infinity.
Infinity.
Right.
And so if I do a number divided by infinity, what does that get closer and closer to?
Infinity.
If I have some number 5 divided by n, and n keeps getting bigger and bigger and bigger, what does this whole thing go to? So I got 5 over 1, 5 over 2, 5 over 3, 5 over 4. Eventually I got 5 over 1,000.
It's getting close to 1, right?
Eventually I'm going to get 5 over 1,000. I'm going to get 5
Zero.
over 1,000.
Zero.
It's closer and closer to 0. The top stays the same, the bottom gets bigger and bigger, the whole thing gets closer and closer to 0.
Right.
So this is over n squared, a really big number times a really big number, and we're dividing it by that. This whole thing goes to 0 really fast. So in the limit, this whole term turns into 0. You see that?
Same infinity.
As n gets arbitrarily big, this whole thing gets arbitrarily small, because n only shows up in the denominator. The numerator gets closer and closer to the circumference part. That's just a number, like 57. The denominator, on the other hand, keeps getting arbitrarily large.
Right.
And since the denominator gets arbitrarily large, the whole thing goes to
Oh.
0.
Right.
There you go.
The limit is 0.
So the limit of this portion is 0.
Right.
So finally, in the limit of a sub n, we get r squared minus 0 all under the square root.
R squared.
Well, r squared, but now take its square root.
R.
R, which we could have guessed from this picture. As we use more and more sides, our apothem gets closer and closer to r.
Right.
Right? When we did a square, our apothem wasn't anywhere close to r. Here we did an octagon. Our apothem is still a ways away from r. Up here, it's getting pretty close to r.
Right.
And as we use more and more sides of our regular polygon, as these triangles get narrower and narrower, our apothem gets closer and closer to r, and in the limit, it is r.
Right.
So, the limit of a sub n is
R.
r. So this is equal to 1/2 times circumference times r. Now we have a formula for circumference that we like to use, 2 pi r. So that's the same thing as 1/2 times 2 pi r times r. Sorry, that's times r. 1/2 and 2 give me 1. So
pi 2r
pi times r, or pi r squared,
is
the area of a circle. So there we go. We calculated the area of the circle. The area of a circle is equal to 1/2 the circumference times the radius. So that's what they want us to prove. So 1/2 circumference times radius gives you the area of a circle. So that's one formula that the author used, and then here's the other formula they want to use. So area equals 1/2 the circumference times the radius, or area equals pi r squared. This is far and away the more common way it comes up. If you were to Google formula for the area of a circle, 9 out of 10 of the formulas would be that. Okay. And that is it for chapter 11. How you guys feeling? Ready to dive into chapter 12? Is limit stuff killing you?
Yeah,
It's not killing me.
Not killing you? I mean, it wasn't exactly a long lecture, but
It wasn't long.
I also don't want to burn you out. We have some cushion time in the semester still.
Yeah.
So let's we'll keep this a softer week because the homework for this week is going to be nothing.
It's, yeah.
So this gives you a good chance to get completely caught up on homework. We'll start chapter 12.
Chapter 11 and chapter 11 is super easy.
Yeah, homework wise should be easy. So lecture wise really hard for you. Homework wise should be easy. And then
All of chapter 11.
next week we'll do chapter 12. We'll be able to get through it in one lecture. And then the week after that we have our
Test.
test.
Oh, that's so perfect.
So can start getting ready for that.
I might be gone that week.